Thank you very much, Sabah and Madhu.
Thank you.
Thank you, Saba.
Thank you.
And let's see, we should now have William Crowson, I believe.
Hello,
Or-
can you hear me?
Oh, yeah, good. And you are a mechanical engineer and a recent graduate from also from Southern California University.
I'm sorry, I'm taking all your spots here, but
You can do the presentation if you want.
no, William Crowson was a very special student in the class. Go for it, Will.
Yeah, floor is yours.
All right, cool. Can you see my slides?
Yes, we can.
All right, perfect. Yeah, shout out to Professor Madhu with his came up with this initial concept mission architecture for the Slinger mission as part of his ASDE 527 class for concept space concept studio design. So today I'll be presenting a very high level concept mission architecture for the SLINGER mission, or Sampling Lunar Interior Natural Geology for an Earth Return mission. The first samples collected on the moon were done so during the Apollo 11 mission in 1969, where Apollo astronauts collected 22 kilograms of lunar samples and successfully brought them back to Earth. Each subsequent Apollo mission after that collected more and more samples until by the end of the Apollo era, they collected almost 400 kilograms of lunar samples for scientists to analyze. In addition to these samples collected by humans, there have also been a handful of successful robotic lunar sample return missions. The first ever successful one was conducted by Russia in 1970, where a Luna 16 lander touched down on the moon, collected 100 grams of samples, and successfully brought it back for analysis. Russia then repeated this similar mission architecture 2 more times, collecting samples from various other locations on the moon throughout the 1970s. More recently, China has begun conducting robot sample missions. In 2020, they had the Chang'e 5 mission that collected almost 2 kilograms of samples from the lunar surface. And in 2024, just under a month ago, they successfully collected almost 2 kilograms of samples from the far side of the moon, being the first country to ever bring back samples from the far side of the moon for analysis. The SLINGER mission concept that I'll be discussing today will strive to collect samples from the interior of the moon's surface, or interior of the moon, inside of the Mare Tranquillitatis pit. The goal is to collect 2 kilograms of samples and bring them back to Earth by 2030. So why even collect samples from the moon? Well, collecting samples helps scientists determine the history of the moon and the inner solar system and how they're formed. And lunar pits specifically are helpful in this because they provide access to older rock layers and areas largely unweathered by solar radiation and micrometeorite bombardment. Collecting samples also allows the evaluation of different resources available inside of lunar pits, as well as the geological stability, which will help with future mission planning and the determination of if these are suitable for future human habitats. Another advantage is that collecting samples can help verify remote sensing data and calibrate lunar orbiting spacecraft measurements, helping make those systems more robust and accurate. Finally, by bringing those samples back to Earth, more sensitive and powerful science equipment can be used, meaning that even a small amount of lunar samples can help unlock large lunar mysteries. In recent years, there's been growing interest again in returning to the moon, and with the advancements in technology and the desire to investigate even harder to reach areas, robotic missions have become popular in literature for proposed mission concepts. There's been a number of concepts, including Globetrotter, which was proposed by Lee and Associates. This concept uses an airbag-based system with thrusters to bound across the lunar surface, potentially going into lunar pits and collecting samples, and then using thrusters to propel itself back out again. the Moon Diver mission proposed by Nesnes and Associates, which uses a tethered-based system to lower a two-wheeled axle rover over the edge of a lunar pit and collect samples from the pit wall. The LIDO mission, which is suggested by Hooper and Associates, that uses a zipline-based system shot across the skylight opening of a pit and then uses that zipline to lower a reconnaissance robot into the pit for mapping and exploration. And then there's the Scarab and Viper missions proposed by Carnegie Mellon and NASA, respectively, where both of these use drilling operations for exploring lunar craters on the South Pole. There are a number of challenges with collecting samples inside of lunar pits, the biggest being how to actually access the interior of the lunar pit. The simple initial solution would be to use retropropulsion to land a vehicle inside of the lunar pits. However, the plumes and exhaust from these thrusters can create contamination risks as well as kick up large dust clouds that can damage science equipment and disrupt landing sensors. Additionally, another option would be to drive in from the surface into the skylight opening. However, the regolith around the pit funnel opening is theorized to be highly unstable, where driving on the surface could trigger rock slides or avalanches that again could contaminate lower samples inside of the lunar pit, as well as potentially damage the rover or even bury it under a pile of rubble. Another major issue or challenge with exploring inside lunar pits is how to maintain communication with the robot while it's inside the pits without direct line of sight to orbiting spacecraft or the Earth. The SLINGER mission concept that I proposed today strives to overcome these challenges by using an initial retropropulsion descent vehicle to slow down the vehicle from lunar orbit and use advanced terrain navigation as demonstrated recently in JAXA's lunar lander to pinpoint locate over the lunar pit opening and hover a safe distance above it. Once it's hovering, it'll deploy an airbag-based system with a reconnaissance rover inside of it. After deploying the airbag, the main descent vehicle will land a safe distance away from the lunar pit opening. The airbag-based system will deploy a communication relay that will communicate with orbiting spacecraft such as the Lunar Reconnaissance Orbiter to help relay information and the initial environmental sensing data back to Earth. The airbag-based system will deploy the sample collecting rover where it'll explore into the lunar pits and lava tubes, collect samples, and it'll place those samples into a canister where they'll be slung to the surface, collected by a canister retrieval unit, brought back to an ascent vehicle, and eventually brought back to Earth for analysis. The rationale for this design is that the initial retropropulsive slows down the vehicle enough to safely aim and land the sample rover using the airbag-based landing system, and the airbag landing system results in less dust and contamination risk than a fully retropropulsive landing would. And the moon's lower gravity and lack of atmosphere makes slinging the sample canister out of the pit to surface a much more favorable option than if it was done, say, here on Earth. Without the influences of air drag and wind gusts, the possible trajectory that the canister will be slung to the surface with can be much more accurate as you take out a large risk factors in affecting the overall trajectory, as well as the moon's 1/6 gravity means that it requires much less energy to get the canister out of the pit and back up to the surface. The Mare Tranquilidad pit was selected for this mission because it sits atop one of the larger confirmed voids on the moon, meaning that there'll be ample area to explore. It also sits on the boundary of two distinct lava flows, meaning that there's two major geological areas that it can sample from, as well as 2 distinct basalt areas that it can evaluate the different resources available for potential future human missions and habitats. After coming up with this initial design, I then calculated a sample trajectory and determined that it would take about 23 meters per second to sling the canister out of the pit and back up to the surface. This is roughly about 50 miles per hour in empirical units, which is pretty close to the speed an average man can throw a baseball at. For a 3-kilogram payload, this would assume a 2-kilogram sample plus a 1-kilogram canister to put it in. It would take about 800 joules to sling the canister up to the surface. With that information, I then did a high-level trade study comparing different slinging options, looking at linear mass driver, catapult, trebuchet, crossbow, motor arm style device, or an air cannon to potentially sling the canister up to the surface. Trade study ultimately landed on a motor arm device, with the main advantages being that it likely require less mass and would be repeatable. However, the major drawback to this solution is that it would likely require a lot of speed to. The way the motor arm would work is that it would spin up the arm holding the canister until it reaches the desired speed and angle, and then release the canister, sling it to the surface, similar to a very small version of the spin launch design, if you're familiar with that company's concept. The major disadvantage of this is that the power and heat generation that it would require. The runner-up concepts would be a crossbow or catapult design, where the major advantage to this is that the power usage would be spread out over a much longer period of time, as the energy is stored into a mechanical system used to sling the canister to the surface. The major drawback to these options, though, is that they would require likely much heavier mass in their vehicle. With that information, I then created this concept diagram to help showcase some of the other potential systems that could be located inside of the sample rover, including the sample launch arm and the sample canister that will be slung to the surface. It could use flash imaging or laser scanning to help navigate inside of the lunar lava tubes. It could use knit and all-wire wheels to help traverse over rough terrain, especially around the pit opening that could have a lot of debris left over from the skylight. It would have a drill and scoop to help collect samples and a spectrometer to help determine where the best location to collect those samples from. It used temp and radiation sensors to help measure the internal environment inside of the lava pits and tubes, so that we can use that information for better planning for future missions. It would use a 6-degree of freedom manipulator arm to help load samples into the canister and into the sample launch arm. And the whole thing could be powered potentially by an advanced Stirling radioisotope generator or some other form of advanced radioisotope generator power source. The advantage of this is that then it can maintain power without relying on solar power options as it's exploring inside of the lava tubes. After fleshing out some of those system concepts, I then looked at some of the other system element details. The descent vehicle could use potentially a hydrazine type of propellant and cold gas thrusters for navigation and descent. This is similar to what China's Chang'e 6 descent vehicle currently uses. The ascent vehicle could use a hypergolic propellant. The main advantage of this is that it's much more reliable in its ignition, as it just uses 2 chemicals that auto-ignite as soon as they come into contact with each other. Again, I think this is similar to what the Chang'e 6 ascent vehicle currently uses for its design. The sample canisters would likely need some sort of RFID locator to help the canister retrieval unit to locate it. This would be similar to like an Apple AirTag type of device inside of the canister to help it locate it. And the canister retrieval unit, since it's located on the surface, could likely be powered by solar power. The communication relays would likely be battery powered, but it could potentially be solar rechargeable, meaning that as the batteries run out, the the sample rover could move them back into the sunlight at the pit opening for recharge, and then move them further into the lava tubes to maintain communication relays. And the airbag system could utilize a combined airbag system newly proposed in a research paper by the Chinese Institute, and I'll flesh out a bit more details on what that means in this next slide. So there are two main types of airbag-based landing systems typically used. There's vented and unvented systems. So an unvented system is similar to what was used in Mars's Pathfinder mission. These systems, when they impact the ground, retain all of their air inside of the airbags. This is a much simpler design. However, you have the drawbacks of the airbags tend to bounce and rebound, making it much harder to tell the orientation that you'll end up in, as well as the location once it stopped rolling around. A vented system is similar to what's used for Orion and Starliner capsules for landing. This system, when it impacts the ground, then it vents the air out into the atmosphere and uses and this creates a cushioning effect that avoids the undesired rebound and bouncing. However, this has the drawback of when being used on the moon, you have the potential that that air, when vented in space, could create contamination risks as well as kick up dust clouds, again, potentially damaging or coating science equipment. So the Chinese Institute, in their paper from Zhao and Associates, has proposed a combined airbag-based landing system where when it impacts the ground, it vents the air out, but into a secondary inflatable-based airbag. This has the benefits of creating that cushioning effect and avoiding rebounds, but also keeps all the air inside to avoid creating large dust clouds. For reference, I calculated what the expected impact velocity could be if you dropped the airbag-based system from 150 meters to the surface. This would be about equivalent to hovering 25 meters above the pit opening, and found that it's about 22 meters per second, which is on par with Mars's Pathfinder mission. This is a bit above the capabilities currently proposed in Zhao's paper. So there'd obviously need to be some further development to make this system work. However, if it was determined that it'd be unusable for this mission, a fallback would be to use the unvented design similar to what was already used on Pathfinders, since the impact velocities are similar in scale. Assumptions and goals for this mission would be that it'd be commercially viable, trying to be low cost, at least relatively speaking, in terms of spacecraft development, and utilize NASA's new push towards commercial development, similar to its commercial lunar payload systems or CLPS that it's using for Artemis. Could fall into one of those categories, using competitive contracts to help with development. And it could also help lower costs by leveraging existing Earth infrastructure as much as possible, such as using the Falcon Heavy launch vehicle to bring the system to the moon, and rely on existing communication systems such as the Lunar Reconnaissance Orbiter or the Lunar Data Network currently being developed by Intuitive Machines. The merits of this design is that you can collect samples from inside of lunar pits using with relatively lower contamination and dust risk. You avoid the unstable pit rim, and you have less on-site assembly than some other proposed concepts. Also, a major advantage to this is that it's repeatable in its sample collection. You could bring multiple canisters with you, collect samples from multiple areas inside of the lunar pit, put those samples in canisters, sling them up to the surface individually, and then collect them using a canister retrieval unit for them all to be placed inside of the ascent vehicle and brought back to Earth together. So you're really just limited by the number of canisters that you bring with you for the number of areas you could sample from inside of the pit. Limitations to this design is that there is a small risk that you could miss the pit opening. However, with JAXA's recent mission, For its lunar lander, it demonstrated the ability to land within tens of meters of accuracy, where the pit opening is closer to 100 meters in diameter, so it's a relatively small risk now. The major limitation of the design is the heat dissipation. A paper from Horvath and Associates theorizes that the Mare Tranquillitatis pit opening, specifically in the skylight area, could be one of the hottest regions on the moon. And for this reason, the power and heat generation required from the slinging motor in its arm could pose a major issue to this design. However, as I mentioned previously in the trade study, there are those alternatives using either the crossbow or catapult type design that spread that heat and power over a longer timeline and could be good alternatives if it proves to be too much for the motor slinging arm. Another drawback is that there are many system elements that need to be developed and work together all at once for the system to work and be successful. However, this does offer some advantages in that you can utilize those trade-offs in the design to potentially lower costs, such as the slinging device may not need to be as accurate if you can make up for it with your canister retrieval unit on the surface, as long as it can traverse the surface and locate sample canisters once it's on the lunar surface. Immediate next steps for this design would be to continue to do trade studies to help refine the system details and calculate the mass and power estimates for each system element. Shown here for reference are the Scarab and Changi mission specifications. The design that I proposed here for the sample collection rover is heavily based off of Carnegie Mellon's Scarab design. So it's, in theory, could be similar to the mass and power here, although once you've added the slinging device, then it'd likely go up in mass as well as power requirements. And also shown here, the Changi 6 reference for launch mass. The ascent vehicle would likely be pretty similar in size for this mission as what's used on Changi 6, so that mass could be used at least for initial estimates. The descent vehicle, however, since it would need to carry the sample rover as well as the airbag system and the canister retrieval unit, would likely be much heavier for the landing descent vehicle. So I don't think it'd be unreasonable, at least as an initial estimate, to assume that it'd be roughly twice as heavy as the current Changi mission. Future studies for this concept beyond those initial steps is if this mission architecture proves to be a viable one, then you can explore the possibility of using this mission architecture to explore other pits and craters on the moon. There are many other areas of interest to scientists and locations for potential future habitats that could be explored. You have the options to potentially look at bringing resupply missions to help extend the life of of the Slinger mission by bringing more canisters, batteries, and relays. They would allow the sample rover to explore even further into lava tubes and collect more samples of areas of interest. And additional studies could be looked at for methods to increase the commercial viability for this mission, such as potentially having the sample rover scratch out the first cave carvings inside of the lunar pit and sell these images as NFTs to help raise funds for the mission. That concludes my presentation. Thank you all.
Thank you, William. Let's see, do we have any no questions there? Need to be better at asking questions. I'm listening. Any questions or comments by anyone? Okay. What is the main hurdle here in order to get this rolling on the moon? What is the? You've talked about a bit about the next steps, but what do you think is the next big part that you need to address?
I think coming up with the making sure that the slinging device would be I think is a major key component to this mission architecture, and is something that's relatively new as far as what I've seen in the literature. So I think that'd be a major something that needs to be investigated further to make sure that it can work properly.
Stable and reliable, yeah.
Right. And that you can shield it from potential dust contamination to avoid wearing down the system as it's used repeatedly.
Or even just being a bit of friction there so it doesn't throw it in the right direction.
Right, yeah, exactly.
Okay, good. Other questions? Oh, no, I haven't replied. Let's see. Oops. Right.
There is a question, Nicholas.
Sorry?
Somebody just posted a question.
Yes, that was a great Malmos. I don't know who that is, but that was a great presentation. Maybe one question is how to ensure a soft landing of the canister on the lunar surface, or is the canister made of a specific material to mitigate potential damage?
Yeah, luckily with the moon's lower gravity and the fact that when you reach the lunar surface, you're near the top of the trajectory peak. So the impact velocities by the time you get up there would be relatively low compared to like if you did this system here on Earth. So that's one major advantage to this design. But yeah, obviously you want to make sure that you can sufficiently build the canisters up so that they won't get dented or buried in dust when they impact the surface. So they'd likely need some sort of Teflon coating and probably some metal or composite structure to help avoid the denting, especially if it happens to land on a rock or something when it hits the surface. So.
There are rocks on the lunar surface. There's a lot of dust, though.
Yeah.
There's another question, actually. Yeah. Thanks from the one asking the question. So that's good. Chris is asking also, any thoughts on cutting gathered samples down to the size and mass to fit in the Slinger capsule? A good question. Or do you just try to find dust?
I think with the drill, so yeah, if you're using the scoop to collect samples, then it'd mostly just be dust on the surface that you'd be piling into the canister. With the drill system, you could take advantage of potentially, I know like with Perseverance or Curiosity with their drill system, it cuts out, circular core samples of a uniform shape and size, at least relatively. And then those can be put into, smaller capsules. So you could potentially, cut out smaller circular cylinder cores and then load multiple of those into the same canister or into smaller canisters for slinging to the surface thing.
Yeah. Makes sense. But yeah, you're considering both. Right. Okay. Yeah, there isn't that much time. So thank you for a nice presentation and an intriguing concept. I like to do caving, so doing it on the moon seems extra attractive, obviously. But let's go for the next presenter.